Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry for the upcoming JEE exam for 45 days. So, in the previous class, we have completed the DNF block. Then, in this class, we will be starting the next chapter, that is the coordination compound. So, the DNF block you studied about in the earlier classes make a special type of compound that is called coordination compound. That means the transition metal that are present there, or the metal ions, make a secondary kind of bond, you can say, which will be explained in the later on slides at how this bonding is formed and what is the structure. And these compounds are called as coordination compound. Since this coordination compound is very useful in many daily life application and for synthetic process also. So this is a very kind of broad area of research in the recent times. Okay, so we will study about this coordination compound. So before that, let us see the JEE syllabus, which is given in the NTA site, and according to that, I have listed all the syllabus that is given. So today we will be covering this four topics, which are introduction part, then the Werner theory, then about the ligands and all terminologies, then how to name this coordination compound. Okay. So in the next class, we will study about the bonding properties, that how these ligands are bonded to the metal ions. So today basically we will be mainly discussing about this IUPAC nomenclature, isomerism, ligands, all the terminologies, and what was the first theory that was given to explain this coordination compound. So this is the today's topic in more diversified way, and each of this will be covered one by one. So today we will covering 7 topics. So if you consider the weightage of this say transition elements and coordination chemistry together, so average are 3 questions are asked in the JEE exams, and it has a 12 marks of average each year. So the first theory that was given, it was given by Warner to explain this coordination compound. What he did is that he reacted this COCl3 6NH3 of different say 5NH3 then 4NH3 with excess Ag plus. Yeah, it did that. And what did he find? That on reacting this on extra with extra Ag plus, it gave 3 AgCl, the first one. The second one gave 2 AgCl, the third one AgCl, and the last one no PPT. So this explains that, okay, so there is a secondary kind of valency which is existing, means say we have this compound here COCl3 6NH3. Then in this there are 3 Cl, this also has 3 Cl, this also has 3 Cl, all 4 have 4 Cl, but the amount of AgCl that is precipitated, or you can say the equivalence of AgCl that is precipitated, is not similar in all of this, although they all of this have the same number of Cl. So it means that the Cl that is precipitated and that one which is remaining in the say salt is different, means they are coordinated different to this cobalt metal ion. So for those who do not know why this AgCl precipitating, so this AgCl is kind of a partially soluble salt, means it is not completely soluble, and when it is dissolved in water, only a very small proportion of this salt is dissolved, and most of this is precipitated, or you can say that settled at the bottom of the beaker. So this was the experiment that Warner did. Now another experiment which supported that this bonding in of all the 3 Cls are not same was this conductometric titration. So in simpler words, you can say they are measuring the conductivity of all these 4 ions. So in the first case, they saw that the ratio of which the means the electrolyte ratio was found to be 1:3, means there are 4 ions that are present in 1 mole of this CONH3, and it has a yellow color. Okay, so this has a yellow color. Now which was the second, which was having 2. Okay, so 1:2, it was 3, sorry, 3 for this purple, and then we have this green and then violet. So green and violet have 2 kinds. Okay, so 1:1 and 1:1. So we will see this one by one. So it is basically about the isomerism. So the main thing that is I want to mainly focus here is that although they have the same number of Cl, so you can see the 3 Cl, it also has 2 and plus 1 3 Cl, it also has 3 Cl, but the say the number of electrolytes or the number of AgCl precipitated is not same, meaning that all these Cl are not coordinated, or you can say bonded to this cobalt ion in a similar fashion. So Warner gave a theory in which he said that There are two types of valency in this coordination compound. The first one is the primary valency, which you are aware about. Means suppose we have a compound, say HCl, then the Cl is having a then Cl is satisfying the primary valency. It is very simple. Or you can say NaCl. If you are considering the metal, then Cl is say satisfying the primary valency as it is say as a charge neutrality function. Now, what is the main difference? So, if you consider a coordination compound, say one coordination compound is given here, which is as CO NH3 whole 6 Cl3, it means that the NH3 is here neutral. Okay, it is neutral and it is satisfying the secondary valency because it is under the coordination sphere, and the Cl3 means it is outside the sphere and it is having the primary valency. Now, what are the how can we say that it is primary, it is secondary? The first one you cannot just say that means it is more boundary line of that, but of course CONH3, that is the primary valence that we have here, is generally positive and 0. So CO can be present, can have a 0 valency or +1 or +2 or like that or further. Okay, so this kind of valency is said to be primary valency, whereas secondary valency is generally the coordination number. So we'll study about this coordination number later on. Now the primary valency is satisfied by negative ions. So this is the main key point here, that the primary valency is always and always satisfied by negative ions, while the secondary valency can be satisfied by both all of this, that is negative, positive or neutral, any of this. Okay. Now the next one is that it is directional in nature. Okay, so this is the direction. So it is written wrong. Sorry. So this one is non-directional and this is directional. Sorry for the confusion. So say this secondary valency, it has a certain direction, means it is oriented in a certain fashion and not in a random fashion. So it is directional in nature. While our ion, or you must have seen that if I have an NaCl, then the Cl minus can be oriented in any fashion. It does not matter anymore. So this is the this is the property of primary valency, that it is non-directional in nature. And one more property it has, that this primary valency is ionizable. Ionizable means it can form ions when it is dissolved in water, and due to this reason only, it is giving a different ratio of the electrolytes, and this one is non-ionizable. So what does this ionizable and non-ionizable means? So if you look at this previous slide here, then you can see that this is satisfying the primary valency. Okay, so sorry, secondary valency, and this is satisfying the primary valency. Now if you dissolve this in water, this whole compound will give 3 moles of Cl minus and 1 this whole compound. Now total of 4 ions are present, and that is the ratio that is given, 1:3. Now if you dissolve this one in water, then it will have 2 Cl minus, means 2 moles of Cl minus and 1 mole of this. So it will have 1:2. Similarly, this is 1:1 and this is also 1:1. So this is the main difference you can say between this primary and secondary valency, that this one is ionizable, means when it is dissolved in water, this Cl minus is like, you can, if you want to see it, like this. So it is COCl3 COCl2. COCl, then NH3 whole 5, then we have this 2Cl minus. So if we dissolve this in water, H2O, then it will give it as COCl NH3 whole 5 2 plus 2Cl minus. Okay, so these are the 3 ions that is giving. It is giving 3 ions. Okay, so you can see very clearly here that it is ionizable, means when it is dissolved in water, it gives one equivalence of this and 2 equivalent of this Cl minus. Okay, now let us move to this thing, that is ligands. So we have seen that something is satisfying the secondary valency, which is having a direction which is directional in nature, and it is non-ionizable. Now these things are called ligands, and there are three types of ligand based on the charge that is present on the ligand. So it can be neutral, anionic, or cationic. So I have told it earlier. So for neutral, we have the example as water, NH3 and CO. For negative, we have the Cl minus, OH minus, Cn minus. Then we have the NH2 plus. It is called amidogen. And then we have nitrosyl. So this is nitrosyl. So these are some examples of charged, uncharged, and say different kind of ligand. So you must be aware about that, because in the exam you get the question that okay, tell the oxidation state and use it the oxidation state to find something that is relevant to question. So for that case, you must remember that which ion, which ligand is charged and which one is not charged, and if it's charged, which one is anion and which one is cation. So if you see the definition, it says that ligands are molecules or ions that can donate a pair of electron to the metal ion. So that thing, this thing is important here, that a ligand can donate a pair of electron. This can be more than one pair depending upon the donor site that the ligand will have. So one donor site will donate one pair of electron. It can also donate more than one in case it is having a bridging. So we will see that is a complicated case. We will see that thing in later on slides. Now let us move to next thing, that is called denticity. So what is denticity? So denticity is basically about the how many donor sites a ligand is having. Okay, so it refers to the number of donor atoms in a ligand, or site, you can say atoms also, that are directly bonded to the central metal ion. So if you look here, we have H2O. Now this H2O has oxygen which has lone pair, and it can donate this lone pair. So it has one site of donation. That is why it is called monodentate. Similarly, it has one. This one has one. Cl minus is alone, so it will be always one, and this is the case. Now if you move to this next, that is bidentate, you can see that two nitrogen atoms are present and both are having lone pair, so they both can donate. So it is called bidentate. Similarly, it is also bidentate, and this is also bidentate. This is C2O4, that is oxalato, and we have acetyl acetone. Now moving to more complex ligands, we have this diethylene triamine, which is having 2 to 3 donor sites. So 3 donor sites are present, and this is the one that is having the most number of donor site, that is EDTA. So it is the most famous example. It is called as ethylene diamine tetraacetate ion, which is having up to 6 donor site. So this has the maximum number of donor site. So no other ligand is found till date that is having 6 donor site. Okay, so this is all about denticity. Now when we talk about denticity, then we talk about the donor sites. Now a special case arises that is called as ambident ligand. So what is ambident ligand? So ambident ligand is one which can donate more than from 2 donor sites, but not simultaneously. So this is the main difference between you can say between ambident and polydentate ligand, is that they can donate electron pair but from 2 different sites or 3 different sites, but the case is that it can not donate it simultaneously. So let us see the example. So here is nitro N and nitro O. So this both are nothing but the resonance structure of each of this. So both are the resonance structure of each other. Now the first one is donating from nitrogen and the second one is donating from oxygen. Similarly, we have this cyno and isocyano. So remember this, if you want to remember it, that whenever it is say changing the donor site, there is iso word used. So the same is the case for thiocyanato and isothiocyanato. Similarly, we have this thiosulfato and thiosulfato S. So you should remember this ambident ligand because it is helped in finding the number of isomers. So it is when the donor sites are changed in a ligand, then it creates a type of isomer. So we will look at this in the later on slides. So the next thing we will see is the coordination number. So I have told you that secondary valency is the coordination number, means the number of secondary valency is called as the coordination number. So if you see here, we have an example that this CN has six, this compound has six, say, ligands, so it will have a coordination number of 6. So this is the compound that we have, another example that we have. So this cobalt has also 6 coordination number because 6 ammonia molecules are coordinated through coordinate bond. Similarly here, this iron also has 6 coordination number as it has 6 cyanide ions, or you can say 6 cyanide ligands. Now if I summarize all those concepts, so we have this, say, whole of this. So the coordination sphere is this, that is present between the braces. So it is called as the coordination sphere. Now this is called the coordination number, which is satisfying the secondary valency. And the molecule or the species which is satisfying the secondary valency are called as ligands. And the metal ion that is present is called as the central atom, which is present inside the coordination sphere. So this should be kept in mind, that the metal ion should be inside the coordination sphere. Then it will only it will call as the, we will call it as the central atom. Otherwise, if it is present outside these braces, or you can say outside the coordination sphere, then it is satisfying the primary valency, and it is also called as counter ion. So in this case, if you want to find the coordination number of Fe, sorry, oxidation number of Fe, so you can find it like this. So we know very well that K has a plus charge. So there are 4. So plus 4. We do not know it for Fe. So overall it is neutral. So it will be equals to 0. Then we do not, let us keep it as X. Then Cn has a minus charge, unit minus charge. 6 or 6 Cn are present here. So it will be minus 6. So X will be equals to 2. So this Fe has an oxidation state of 2. So in this way, you can find the oxidation state of a given metal in a given coordination compound. Now let us move to a very interesting concept that is called as chelation. So what is this chelation? You can see an example of chelation here. So basically in chelation, we can see a formation of ring is here. Okay, so whenever we are replacing a monodentate ligand with a bidentate ligand, then we form kind of ring. So this is a kind of ring that is formed here. So this is the example of ethylene diamine tetraacetate that we have talked earlier about. Suppose this is the metal ion we have that is having 6 unidentate ligand. So 1, 2, 3, 4, 5, 6. Now we are replacing all the 6 one at a time by reacting it with EDTA. So all the metal ions, all the ligands will be replaced by this EDTA, and EDTA will simultaneously donate from all its 6 donor sites. Now why is this chelation effect very important? Because the compound that is formed after the chelation effect is much more stable than this compound which is having only unidentate ligand. Why is it so? So let us see the reason behind it. So suppose this is the reaction that we have here. So this metal ion that we have here is CO, for example, and all these ligands are H2O. Okay, now we are changing this ligand also that we are replacing. We are taking it as C2O4 2 minus. Now after the reaction, say one C2O42 has 2 donor sites. So we have seen it earlier also that it is a bidentate. Now if we have 6 H2O, then 3 C2O4 can easily replace this 6 H2O because 1 has 2. So 3 into 2, 6. So this is the whole of the reaction. Now if you look here, on the reactant side we have 4 reactant particles, and on the product side we have 6 product particles. Now you know very well that inotropy is nothing but randomness, or you can say as the number of particles increase, the entropy will of course increase. So that's why there is an entropy increase when the reaction is going from this left side to right side, that is removal of unidentate ligand to bidentate or tetradentate or hexadentate. No matter if the denticity is increased of a ligand, then the reaction will be having inotropy increase. Now due to this inotropy increase, this reaction become feasible and the products become thermodynamically stable. So this product is thermodynamically stable. So this is called at the chelation or the chelate effect. Now let us move to this IUPAC nomenclature. So we need to name this coordination compound. So there are very simple rules for it. So the first rule says that we have to first identify which is the ligand and which is the metal center. Then second one, we will keep this ligand name in alphabetical order. So suppose we have two names, so one starting with A and second is starting with B, then we will keep the one which is starting with A in the first and then with B in the second. After that we will keep the metal ion name, okay, metal center name. And if the ligand that we are having is having a negative charge, then we will add O to this end name. So suppose we have chloride, we know very well that chloride is negatively charged, then we will call it as chlorido. Similarly, if we have bromide, then bromido. And at the last, we add the word ion after the ligand's name. Now, if we have more than say 2 or 3 or the similar kind of presence of 2 or 3 ligands, then we will call it as bis tris. So we will see the example, it will make it more clear. So this is the example that we have here. So we can see very clearly that we are having 6 ammonia. So it will be hexaamine cobalt 3 chloride. Okay. Now here also, so here the amine that we have here is having no negative charge, so it will be named as it is. Now in second case we have this 2CN. So since we are cyanide is carrying a negative charge, we will keep it as cyanido. So two cyanide ion present here, so we'll name it as dicyanido copper. Now the one thing to notice here is that we are writing this oxidation number of the central metal ion after the name of the metal ion. So you should write this as it is standard IPC nomenclature. Now suppose this is having a say we are having a two bidentate ligand, that in that case we will name it as iron trisoxalate ion. So in this way you can name the coordination compounds. Okay. So this tris word is used. Why is it used? So make it clear. So suppose you have a name that is diethene. So suppose this ligand name is already containing a di. Okay. So you cannot write that, okay, like we are having this CN. So we are placing a di before this cyanido and we are saying it as dicyanido. For this case we cannot place a di here because it will make confusion. So it will make confuse you. So for that IUPAC has find a way. So we have this bis. So suppose if two diethane are present, we will call it as bis diethane. Similarly, we have tris for 3. Then we have tetrakis for 4. Okay. So the ligand name which is already containing di, tri or something like that, then we will replace this di, tri with bis, tris and tetrakis. Now let us move to isomerism. So a coordination compound can show two types of isomerism basically. The first one is stereoisomer. So it is basically due to the spatial arrangement of the ligands in the 3D space. The second one is the structural isomerism. So it is due to mainly to the change in the structure of the compound. Now geometrical isomers are of two types. The first one is the stereoisomers are the two types. First one is the geometrical isomer. So it can have all cis and trans. So we have this cisplatin and transplatin. Then we have this optical isomer, that is DL configuration. Now structural isomer can be of 4 types, that are solvate isomers. So basically in solvate isomers, the number of ligands that is outside the sphere is changing. You can see very well that this H2O is having 6 H2O we are having, and Cl3 are 3. Now if we take one H2O outside and take one Cl inside, then it will be an isomer having the same molecular formula but different structure. Similarly, we have this example of of removing one more water and bringing in one more Cl ion. So this is the solvate isomerism. Then we have this linkage isomer. So it happens mainly due to the linkage of the ambident ligand. So if a compound, say we have NCS, and then we have this CNS. Okay, so cyanito and isocyanito. So it can link through two different sites. So if two compounds are having the same molecular formula but the ambident ligand is linking from two different sites, then we will call it as linkage isomers. Then we have this coordination isomer. So in coordination isomer, the thing is that this is the example of coordination isomer. So suppose a coordination compound is present here, which is like this. So this is a double salt, CrSCN6. Okay. Now, suppose we interchange this metals. Okay, so this is a whole coordination compound. So do not get confused. So suppose this is having the this is the cationic part of the coordination compound, and this is the anionic part of the coordination compound. Now, if these both are interchanged, this metal ion are interchanged, then the molecular formula will be same, but the metal ion that is in the cationic part will be interchanged with the metal ion in the anionic part, and we will get this second coordination compound, which is CrNH3 whole 6. Now Cr is attached to NH3. Initially CO was an H2 attached to NH3. Okay, so these both are coordination isomers. So in coordination isomerism, basically we are changing the metal ion. Then we are having the ionization isomerism. So simply we are replacing the ligands or interchanging the ligands from the primary valency. So we have this four type of structural isomers. Now the stereoisomer has one more type, which is called as facial and meridional. So if three NO2 are present and forming a rectangle or triangle like this, so if this is the case, it is forming a triangle, you can see very clearly, then it will be called as facial. So basically it is forming a kind of face here. And if we take this three, so it is not forming a face, triangular face, so it is called as a meridional. So this is all about isomerism. Now the main question that is asked in the isomerism part is that you have to see that which coordination compound has how many types of isomers and what is the number of enantiomers that it has. So for that I have just prepared a table here. So take a screenshot of all this table and you have to remember it, and then and only then you will be able to remember this number of stereoisomers and pair of enantiomers. So if you look at this table, so the one that is having no number of enantiomer but having stereoisomer, it means that it is due to geometrical isomerism. Okay, so this is the case. Similarly, we have this. So you should remember all this table. There are three tables only, and questions are of course asked from it. And this ABCD mainly represents that these are unidentate ligand. Okay, so we are having unidentate ligand as ABCD. So all these are having different types. So ABCDEF. Now this is the case. Then when we are having, say when we are having a bidentate ligand, but both the donor sites are same. So AA bidentate and same donor site. Okay. So this is the example of a bidentate ligand, but the donor sites are different, B and C. So you must have understood what is the logic behind it. Now similarly, we have an AB which is one ligand having two donor sites. Then both are different. Okay, so this was all about the isomerism part. So for isomerism, you must remember this chart, this all three charts, and you will be easily able to answer the number of isomerism. So this was all for today's class. Now we will solve questions in tomorrow class. Okay. So these are the questions. If you want, you can try it by yourself. When we solve it, you can verify your answers. Okay. Thank you for today's joining today's class.